Okay, hello. So today I'm going to do something a little different than I normally do on this channel. This will not be an accessible math video. This will just be me talking about a paper that I like. And I'll do it in multiple parts so that the videos are short. Um, I'm going to talk about this paper called Cocycle Categories by Jardine. Cocycle categories are supposed to be a way to deal with homotopy maps in the homotopy category of a model category. Um, and I'll explain more what they're good for later. But today I'll just do sort of the setup for the paper and prove that the cocycle category is a weak equivalence invariant, or at least the pi zero of it is. So the setup for this paper is a right proper model category whose weak equivalences are closed under finite products. So I'll just start by reminding you what all those things are. A model category in general is just a category that has all co-limits and all finite limits. And it has three distinguished classes of maps: the weak equivalences, cofibrations, and fibrations. And I'll use fancy arrows for the cofibrations and fibrations. I don't know if people still do that, but I do. Okay, and they satisfy five axioms. One of them is closed under colimits and finite limits. The next is that weak equivalences should satisfy the 2 out of 3 property. So if I have FG and F composed with G, if two of them are weak equivalences, so is the third one. Another property that we should have is that all three of these subcategories are closed under retracts. So remember a retract. Okay, so this outside square here's a fancy way of saying this, is F is a retract of G if the identity arrow in the arrow category factors through G. So that's a good way to remember what it means for F to be a retract of G, is to just package it like that. But F is a retract of G if I have an R, S, I, and J with a diagram like this. But that's the same as saying the identity arrow on F factors through G. Now, cofibrations and fibrations should have this sort of lifting property. That is, if I have a square where the right side is a fibration and the left side is a cofibration, if either one of these is also a weak equivalence, then I get to lift the bottom map from Y to X. Okay, that's M4. And then finally, M5 is any map factors as a fibration and a trivial cofibration. So here's a P, a fibration, and I, a trivial cofibration. Or it can be factored into a trivial fibration and a cofibration. And any map should be able to be factored that way, not necessarily uniquely or functorially or anything like that, but just there exists such a factorization. Okay, now these sort of extra properties, those are all the axioms of a model category. Then we're going to ask for some extra properties. Right proper is what we're going to ask for. So right proper means weak equivalences are stable under pullbacks along fibrations. So here's my fibration. If I take a weak equivalence and I form a pullback square with a weak equivalence and a fibration, then A should still be a weak equivalence. And by the way, also, the top is still going to be a fibration. That's just from model category. Just for completeness, I'll define left proper as well. Left proper means weak equivalences are stable along pushouts, or stable under pushouts along cofibrations. So I have a weak equivalence, I push it out by G, I should get that B is a weak equivalence. That's left proper. If I'm left and right proper, I just say I'm proper. Just a note is that fibrations can be characterized as exactly the maps that have the right lifting property with respect to trivial cofibrations. So if I have this square, this property that fibrations and cofibrations have actually characterizes them, that's a theorem you can prove using just the other axioms of a model category. So a map is a fibration if and only if whenever I have a trivial cofibration here, I can lift this diagram uniquely. And a map is a cofibration if and only if whenever I have a fibration over on the other side, I can lift this diagram. And I can also move the word trivial to the other side. A trivial fibration, meaning a fibration and a weak equivalence, is the same thing as being a map that has the right lifting property with respect to all cofibrations. Now, right lifting properties in general, if I have a right lifting property, like we say P has the right lifting property with respect to trivial cofibrations, any right lifting property is preserved by pullbacks, and any left lifting property, such as the one that defines cofibrations, is preserved by pushouts. Can prove that. And so that means that whenever I form a pushout of a cofibration, I get a cofibration, and a pullback of a fibration is always a fibration. Okay, hopefully my computer can handle this because it has a hard time. Okay, and then the other extra property we're going to ask for besides right proper is closed under finite products. So the weak equivalences of a model category are said to be closed under finite products if whenever I have F a weak equivalence and I take the product with the identity map on any object Z, that's still a weak equivalence for any Z. That's closed under finite products. Okay, so now let's define the cocycle category. Take a model category, take two objects X and Y. I can form the cocycle category. The objects of the cocycle category are these spans. So some object with a map to X and a map to Y, where the map to X is a weak equivalence. And then the morphisms in the cocycle category are morphisms of spans. It's just a map between the two middle objects that commutes with the outside legs. All right, and so the theorem, the only thing I'm going to do today, and I'll cut the video off, is the cocycle category only depends on the weak equivalence type of X and Y. And I'm actually going to prove something weaker. I'm going to prove that the pi zero of h of xy only depends on the weak equivalence type of xy. But I think h of xy should be the same as a simplicial set if I replace x with something weakly equivalent to it and y with something weakly equivalent to it. But let's just do the pi zero. So I'm saying if I have a weak equivalence from x to x prime and a weak equivalence from y to y prime, then that induces a bijection between the pi zero of h of xy and the pi zero of h of x prime y prime. Okay, so let's prove that. I need to construct a map from the cocycle category. I'll construct the backwards one first. I'm going to take a cocycle between x prime and y prime, and I'm going to construct a cocycle from x to y. So firstly, a cocycle is the same as a map from the middle thing into the product, as long as my model category is closed under finite limits, so it certainly has products. And F is a weak equivalence. So then I have this map F comma G, and I can factor it because I can factor any map into a fibration and a trivial cofibration. So J is a trivial cofibration, and Px prime, Py prime will be my fibration. But then because I have this diagram that only has J and Px prime in it, and just goes to x prime, and F is a weak equivalence, and J being a trivial cofibration is a weak equivalence, that implies that Px prime is a weak equivalence. So now I have this map, Px prime, Py prime. It's a fibration, and one of its legs is a weak equivalence. Now I also have a weak equivalence from alpha and beta. So using closed under finite products, I get that alpha cross the identity on y is a weak equivalence, and the identity on x prime cross beta is a weak equivalence. And so their composition is a weak equivalence, and their composition is exactly alpha cross beta. from x cross y to x prime cross y prime. So we get that that's a weak equivalence. I think my pen is not working anymore, so let me try the laser pointer. Is that going to work? Yeah, okay. The laser pointer will work for another few seconds. Okay, now I'm going to form the pullback. I have a weak equivalence, alpha cross beta, and I have a fibration, and I'm going to form the pullback. And because I'm in a right proper model category, when I pull back along a fibration, I get a weak equivalence. So alpha cross beta star is a weak equivalence. And then because fibrations pull back to fibrations, if I call this, I don't know why, Jardine calls it W upper star, the pullback map to x cross y, which we'll call px star, py star, is a fibration also. And then we also know that px star is a weak equivalence because if I compose with PR1 and I just take the map to x and the map to x prime, well, this thing on the upper side of the square is a weak equivalence. Px prime is a weak equivalence, as we saw just a second ago, and alpha is a weak equivalence. So this thing in the middle, that's a weak equivalence. The 2 out of 3 property says px prime is, px star is a weak equivalence. So that tells me that I have an actual cocycle. So that's the construction. That's how we get from a cocycle from x prime y prime to a cocycle from x to y. Now we have to, we wanted a map on pi 0. So we have to check that this is actually a well-defined map on pi 0 of the cocycle category. So let me call that map, let me call this map delta. And let's suppose that I started with a path in the cocycle category, meaning some morphism, and I have to show that it's that it's independent of this. So I won't do a general path. I'll just do a single morphism in the cocycle category and show that I get something in the same path component of the cocycle category. So if I have this, did I call the map phi? Yeah, okay. So if I have this phi, I get 2 decompositions of fg and f prime g prime into fibrations and trivial cofibrations. And then I'll sort of rearrange this diagram. So I have this map J prime composed with phi, goes from Z to W prime. I'll put that on top. And then on this side, I have the fibration from W prime to X prime cross Y prime. And on this side, I have this other fibration. Okay, and then the map from Z to W is a cofibration. This square commutes. And so since I have a trivial cofibration J and a fibration on the right-hand side, I get to lift this to a map from W to W prime. And the bottom square commutes, so that tells me Qx prime L is Px prime, and Qy prime L is Py prime. Okay, so then I also get to form these 2 pullback squares. One of them I'll call the pullback square that I form with alpha cross beta and the Qx prime, Qy prime. I'll call that W star prime. So that's one pullback square I get to form. And then I get to form another pullback square using W star and W. It's the same one as we had before, and alpha cross beta. And so actually, this, let's see. If I took the map from W to X prime cross Y prime, I would get a pullback square up here. But let's not do that. Okay, so I have this pullback square. I have the lift that I constructed from W to W prime, and then I also have alpha cross beta star. And I can compose these and check that this outer path commutes, which I'll do on the next slide. And if it does, then I get a unique map from W star to W star prime, which I'll call Q, because this was a pullback square. So let's check that all that works. The outside legs of the thing we're gonna use the universal property to pull back on commute because qx prime L was px prime, and then because the square with w star and w was a pullback square not commuted, I have that px prime times this weak equivalence on the top was alpha px star, and similarly for the qy prime and beta. So that tells me that this thing I marked, these outside legs I marked in red, that those commute, and so I get the unique lift Q. And Q satisfies that qx star qy star composed with Q equals px star py star. That's commutativity of I think this triangle right here. This map is qx star qy star, which I forgot to label. Okay, and in particular, that means qx star q is px star, etc. But that says that I get a morphism in the Cocycle category from x to y, because delta of f comma g is px star py star, and delta of f prime comma g prime is qx star qy star. And so I have this morphism q in the Cocycle category. So delta sends a path in the Cocycle category to a nice path. So delta is well defined. Okay, now let's do the other one, which is easier. Let's suppose I have an xy cocycle. Well, then I have these nice weak equivalences, so I can just stick them on the ends. And that gives me an x prime y prime cocycle. This is obviously well defined because, again, if I have a morphism in the cocycle category, I just stick them on the ends. Any path, just stick alpha and beta on the two ends. I get a morphism in the x prime y prime cocycle category. So that one's easy. But we have to check that if I call that map gamma, that gamma composed with delta is the identity, and that delta composed with gamma is the identity, and then we'll be done for the day. So let's start with an x prime y prime cocycle. Apply delta, I get this pullback square, something with weak equivalence. I just apply alpha on one side and beta on the other side, and I get this x prime y prime cocycle. I have to show it's in the same path component as the original f comma g, because I want it to be the identity on path components of x prime y prime. So what I'll do is I have this pullback square from forming delta of f comma g, and I have this object z where I decompose that I pass I passed fg through. I'm going to use this to form a path in the cocycle category because I want a map. Let's see, what do I want to map from? I want a map from z to w star, or maybe a map from w star to z, or at least a couple of paths connecting them. So this gives me a map from z to x prime cross y prime, and a map from z to w. But let's see, my map from z to x prime y prime was my original fg. And then my map from z to w satisfied that px prime j was f and py prime j was g, and px prime was a weak equivalence. So that gives me this middle cocycle here with w in the middle. Okay, and then I also have a map from w star to w, and alpha px star and beta py star were the maps that we wanted to form a path with. And I can check that if I take, and actually I think I already did this, if I take alpha cross beta star and apply it after, oops, excuse me, and apply it before px prime, then I should get alpha px star. So that gives me a morphism in the cocycle category. So there we go, z and w star with these two maps are in the same path component of h of x prime y prime. Then let's do the other one. Oh, that's what I just said, basically, I think. Yeah. Okay, so now let's do gamma and then delta. So first I'll apply gamma, which is just sticking alpha and beta on the ends. And then I'll apply delta, which is forming this pullback square using z, w, and all those things. I get a cocycle from x to y. I want to show that it's in the same path component as f comma g. So I have this triangle where alpha f and beta g can be decomposed into a fibration and a trivial cofibration. And it satisfies beta g equals py prime j and alpha f equals px prime j. And then I can form the pullback. So there we go, there's my pullback. And then notice that since px prime j equals alpha f and py prime j equals beta g, the outside legs give me a commuting square thing. And so I get a unique map P from Z to W star because this W star was a pullback. And it commutes, all these things commute. So what is, I think maybe I should have, I think I called something L, but I should have called P. So here, this map is supposed to be called P. Px prime, Py prime, P is Fg by commutativity of this triangle here. That my pen has stopped working again, but it's almost over, so I don't care. This triangle, commutativity of this triangle gives me that, and so that gives me a cocycle morphism between Z and W star. Okay, so there we go. We've showed both the compositions are the identity, so gamma and delta are inverse bijections. That's what we wanted to show. So we're done. Okay, hope you enjoyed it. I will do more later.